Last class I introduced the chain rule. It's a very powerful, very useful, and important shortcut for taking derivatives. It helps you take all sorts of derivatives and think about differentiation in some useful ways. In this video, I'll do a few examples where we'll see the chain rule being put to use, and I'll do a bunch more examples in class on Monday. So here's the chain rule. It applies to composite functions, where we have a chain of functions acting. So we start with x, then we do g to it, then we do f to it. So what would the derivative of this composite function be? Well, you would take the derivative of f with respect to the inner function, so you leave the inner function alone, times the derivative of the outer function. And this equation, I think, is much easier to think about in terms of words and not symbols. So what you do is you take the derivative of the outer function, pretending the inner function is constant, and then you multiply that by the derivative of the inner function. So when I'm doing these, I'm sort of hearing this in my head as opposed to seeing this equation. And I think that's the way most people do it. They think of it procedurally in this way. All right, so let's do an example. Here, suppose you need to take the derivative of 2 plus 3x squared, whole thing to the 3/2. So the first thing I need to do is I need to take the derivative of the outer function with respect to the inner function. So the inner function is 2 plus 3x, and the outer function is blah to the 3/2. So the derivative of blah to the 3/2 is 3/2 blah to the 3/2 minus 1. Then I need to multiply that by the derivative of the inner function. That's the thing formerly known as blah. So the derivative of the inner function, that's the derivative of 2 plus 3x squared. Derivative of 2 is 0. Derivative of 3x squared, let's see, that's 3 times 2x. Derivative of x squared is 2x, and the 3 just goes along for the ride. So let's see, if I simplify this a little bit, these 2's cancel, the 3's give me 9. I've got 9x, 2 plus 3x squared. 3/2 minus 1 is 1/2. So that would be the answer. Let me do one more example, and this one is a little bit more abstract. Suppose we need to take the derivative not of f of x, but of f of x squared. And in this setting, we don't know yet what f of x is. So again, we have an inner and an outer function. The inner function is x squared. The outer function is f. So to take the derivative using the chain rule, first I take the derivative of the outer function, leaving the inner function alone. The derivative of the outer function, I don't really know what it is. It's just f prime. And I leave the inner function alone. I pretend it's constant. So that's f prime of x squared. Then I need to multiply that by the derivative of the inner function, which is 2x. So I could write this. This is 2x f prime of x squared. So this is a general result. This would be true for any f. We could also imagine having this situation, but where the inner and outer functions were reversed. So I could have f of x squared. So for this one, f of x is now the inner function, and squaring is the outer function. So let's apply the chain rule like before. It's just our inner and outer functions are reversed. So the outer function here is squaring. So this is blah squared. The derivative of blah squared is 2 blah. Derivative of 2x. Sorry, derivative of x squared is 2x. Derivative of blah squared is 2 blah. Blah is f of x. Then we're not done. We need to multiply it by the derivative of the inner function. The inner function in this example is f of x, so its derivative is f primed. So this example is a little bit more abstract because we're doing it for general f, but it's a good way of making sure you understand the chain rule, and this sort of thing does come up sometimes as well, so there's some practical use to this. And it also highlights that the order of the functions matter. So here the inner is squared, the outer is f. Here the inner is f and the outer is squared, and you get different things, which makes sense because they're different functions.